You had to do it because I got these unidentified homeworks. And I didn't put your name on, so I need to know which is yours. Gotcha. That says it. Thank you. And here you can take it. And here are your homeworks.
Thank you.
And I forgot to hand out the hard copies of homework. If anybody wants them, they're here. And your quizzes. Okay, I want to remind you that a week from today we have our midterm. And I want to talk a little bit about plan going forward on that.
Is your mic working?
We'll see.
We'll see.
And so I posted in the, I don't know if it's working or not. Is it?
Yeah, a little bit. Yeah, that's good.
It's up high on here. So.
Yeah. Thank you.
So I posted in the figures files on Canvas the outline for the second midterm. So here it is. We covered quite a bit of ground. This is first, so here's where the coverage will start. Here with properties of multi-component systems. And here's what we covered in that. So quite a bit. Detailed outline, I think this should help you in reviewing for the midterm. It'll be, the format for the midterm is the same as for the first one. Probably be some shorter questions, but it'll be comprehensive on this material that we've covered since the first midterm. And my plan going forward is as follows. I'll finish up with the lectures tomorrow. And then Friday we're just gonna go over the homework, which is you're working on right now. And that'll probably leave us some extra time for Q&A on Friday if you want to use it, but I'll also use Monday for that, since you made pretty good use of it last time. So I'll plan Monday, not any new material. So I want to slow things down a bit as we approach this midterm to give you a chance to study and get everything together. So any questions or anything about that, about our plans? Okay, we've got some unfinished business with these flash calculations. So let me go back to the beginning on that, see if I can get PowerPoint to work. That's always questionable. I'm sure this is the thing to make it work too. So this is the situation. What we've got is a feed coming in. We don't really care what its phase state is. And it's some composition here given by the Z's. And when it goes into a flash drum, we hope that it will split into a vapor and a liquid phase. And the flash drum will be at some maintained temperature and pressure. And the vapor fraction goes out as this capital strip V, and the liquid fraction we're taking as L. And we've got, as per usual, the vapor mole fractions are designated as Y's and the liquid mole fractions as X's. Now the typical problem for a flash calculation is where we're given the feed composition and a given temperature and pressure of the flash drum, and we're asked to determine what the phase split is. That is, how much of it ends up being vapor and how much of it being liquid, and what the compositions of those two phases are. And we should note that other formulations are possible. It needn't be this, but this is the typical problem. So we proceed to solve this problem. It's a little bit different than the standard ones where we're given one of the physical variables and the composition of one of the phases, and we want to find the other physical variable and the composition of the other phase. That's our typical PLE problems that we've been dealing with so far, so this is a little bit different. First, we have to make sure that we actually have a solvable problem, that is that we get a phase split. And here's a diagram for a binary system that shows constant temperature or constant pressure system. In the constant temperature system, we've got dew point and bubble point pressure curves which delineate the two-phase region, which is that which is in between. So if I have a composition of my feed to the flash, then we have to require that the flash pressure for a given temperature lies somewhere between the dew point and bubble point pressures in order for us to be ending up in the two-phase region. And when we do, we can see graphically what the problem is. Because we'll go up here to the particular pressure that we have, let's say, and then we want this phase split, so we want to know how much of each. That's given by the lever rule, and then we get the composition of the liquid phase and the vapor phase as the termini of the particular phase line or tie line. If I have, on the other hand, a constant pressure set of curves, I'm fixing both the temperature and the pressure in the flash drum. But then what I have to assure myself is that for the particular composition I have, that I'm going to lie between the dew point and bubble point temperatures. Everyone sort of see that, and again, we would get a tie line that would give us the solution to the problem. So that's kind of the overall situation that we look for a binary. If we have more than that number of components, we can't conveniently draw the situation. So I want to set up a calculation procedure that will work for any number of components. So the problem is solved using a combination of material balances and equilibrium equations. And the overall material balance just tells us that the sum of the liquid and vapor mole fractions is 1. And right away we'll eliminate the liquid mole fraction and express it in terms of the vapor one. So the liquid fraction is just 1 minus V. Then for any and all of the components I, Zi is going to be Xi times the liquid fraction plus Yi times the vapor fraction. And I can write that just substituting in the overall material balance that I've written above. So Zi is just equal to Xi times 1 minus V plus Yi V. Fairly evident. Then the equilibrium equations are conveniently formulated using the K formulation. So I can just write Yi equal Kxi. And this K factor will depend on the situation. It's going to embrace all of the descriptors of the vapor-liquid equilibrium that we might have. If the Lewis and Randolph rule holds, and a subset of the Lewis and Randolph rule is Raoult's law, if that holds, then it's very nice because we have the K's are just constant at a given temperature and pressure. Because the K's are expressible here as as the vapor pressure, the Ki is vapor pressure component I over the total pressure. Total pressure is one of the given fixed values that specify the conditions in the flash drum. But if that isn't the case, then then we have to account for variations, and we aren't going to get anything worse than the modified Raoult's law, but that's bad enough, because then these K factors involve these these activity coefficients, which are functions of the liquid composition, which makes things a bit tougher. Now let's proceed in an orderly way with how we will solve this problem, knowing that what we want to get is V and then the compositions of both the phases. So the solution proceeds as follows. First, we substitute for Xi in all of the component material balances using the equilibrium equation. So Xi in each case is just Yi over K. And then we go to the component material balance equations, and I get Zi ultimately is equal to Yi over Ki, 1 minus V plus Yiv. So that each of the Yi's can just rearrange that, looks like this. So if I knew what the vapor phase fraction was and I knew the KIs, I could solve it right now. But the solution is obtained by summing these mole fractions in the vapor phase equal to 1. So this is the equation that I will solve for V. So I will solve the root for V and proceed from there. If it's a binary, this equation just looks like this. But again, I still, when I plug in for everything, I need to find a root, which would be the root for V. So once V is solved for, I can go back and do these equations and solve for all the y's, and then use the equilibrium equations to solve for all the x's, and the problem is done. So I've solved for the root at this point, and I note that if the k's are constant, the problem is already solved. I've got V, and then all the y's are solved from these equations, and the x's are then solved from the equilibrium equations in terms of these constant k values. And this is a situation you have in your homework problem. However, if we have a more complicated situation, then we have to set up an iterative scheme. So we start by creating an initial set of k's, ki's, as follows. We could do this, a couple ways to do this, but probably the quickest way is to get a start on values of k. We'll set all of the x's, small fractions in the liquid phase, equal to the z's, which are given. And that'll give us a provisional set of activity coefficients to get going. Once we have that set of activity coefficients, I can go back and solve for all of the k's. And this will give me a starting set of k values. So can you see that? Once I have that starting set of k values, I set up the iteration as follows. I solve for V, as I've indicated, now with this provisional set of k values. They could be pretty far off when what the final result is going to be. So we have to note a couple of possibilities. It may turn out that the root you get to this equation for the very beginning turns out to be suggesting that the volume fraction is less than 0. And if that's the case, then you plug in 0 for the next iteration. Or it may turn out that your first root will give you a value of V here greater than 1. And if that's the situation, then you plug in V equal 1 for the next iteration, and then proceed to iterate to convergence. Well, once you've done that, you plug in the value of V, then you solve for all the yi. Once you've got the yi, you can solve for the xi, and that'll give you a new set of gamma I using something that we've got here, Margulis, Van Laar, Wilson parameters, which give us what the activity coefficients are as a function of liquid composition. And then you get a new set of k's and go back and do it all over again and iterate this to convergence. So if you have a binary system, then your spreadsheet should have the following columns. These are going to start out with, well, it doesn't seem to want to let me do anything. K1, my initial values. Then I get the first root for V here and proceed on. And from then on, I get provisional values of K that will take me eventually to constancy and everything.
Can you go back one slide real quick?
I hope so.
Are we calculating an initial set of gamma i's or yi's in that you have underlined there?
Those are gamma i's.
Okay. If you said when you said
So
xi
all
equals
the xi
okay.
equals zi, and then we can calculate, since we have provisional set of xi, we can calculate the gammas.
How would we get the
We have
ki's?
knowledge of gammas as a function of liquid composition. That's the presumption.
How would we get the ki's? Use a nomogram.
Well, that
Nomograph?
could be one thing, but I'm talking now where we have gammas. In the nomograph was where we don't have gammas. That's where we have the Lewis and Randolph rule holding in both phases.
Okay. I just don't
So
you
we
need,
have Van Laar constants, or we have Margulis constants, or Wilson parameters, so that we can calculate the gammas, once we know the liquid composition.
okay.
And when we calculate the gammas, we can go back and calculate the Ks. So we get an initial set, and we start with that, find a root for V, solve for the Ys, then solve for the X's, then get a set of gammas, then a new set of Ks, and iterate that convergence. The example system here is MEK and toluene. Let's say with a feed that is equimolar, so Z1 and Z2 are both 0.5. And let's let our flash drum be at 50 degrees C and the flash pressure at 24 kilopascals. And so what we typically want to solve for here is what the vapor fraction is and what the composition in both the vapor and liquid phases are, which amounts to getting one of them in the fractions in this binary system. So at 50 degrees C, this is the temperature of the flash drum. The vapor pressures are given here. And the activity coefficient, let's say that we have knowledge of them through Margulis equations. And this is what they are for the MEK toluene system. So we put the xi's initially equal to the zi's, that would put them both at 0.5. That allows us to use these equations to calculate the initial values of the activity coefficients, so we can get started calculating the initial value of K1, 1.58, and K2 here turns out to be 0.5612. So that gets us going. And then the whole iteration looks like this, where I put all of the information on my spreadsheet. But here was the K1 and K2 values that I just calculated to get started. When I do that, I solve for the root here for the V. Turns out it's 0.2734. Then I can calculate Y1 and Y2, from which I can get X1 and X2, and then the new gamma 1 and gamma 2. I'm sorry, the gamma 1 and the gamma 2, which allows me to calculate a new set of values for the Ks, and so on to convergence, which ultimately gives us here that volume fraction here, little over 0.3, mole fraction of 1 in the vapor phase, 0.6818, and so on. Yeah.
Do you solve for the root to find V in each iteration? Or do you assume that it stays at 0.3047 after you get it?
No, that was just a coincidence.
Okay.
So I found the root each time.
Okay.
It's interesting how that converts so quickly. Anything else on this, how you would do that? Well, this was a binary system, so we can represent the whole thing graphically. And here it is, I've got the diagram here for constant pressure. So what I've got here are, I'm sorry, constant temperature. So what I've got here are bubble point pressure and dew point pressure curve. And here's my initial composition. The pressure that I set was 24 kilopascals, so here's where I am. So there's my tie line, and it will split up as indicated here. Remember, the vapor phase is about 30%, so that was the length of this line segment divided by the whole length should give me what my V fraction is, and so on. So you could have solved this problem graphically by actually calculating the entire dew point and bubble point pressure curves and then doing it just as I've indicated here graphically using ultimately the lever rule. But of course that isn't possible when you have more than two components. So I showed you a general procedure which would work all the time. And this may be one of the first kind of problems you do in your Transport 3 class when you study distillation. What we've looked at here is what we call a single stage flash, but it's important to understand that we can stage it by putting one after the other. We take the vapor phase out of the first flash and then put it into one above and then re-flash it and so on and so on and so on up the line until we get a higher and higher enrichment of the lighter components as we go to higher stages on up. And conversely, as we move down in stages below, we take the bottoms product here and split that up and so on down the line, ending up finally with product purities, the heavies and the lights, as great as we want, depending on the number of stages that we want to use. And this is a whole process of calculations that you will learn, which is referred to as staging. So what this is just a schematic diagram of a distillation column that you will study here in CHEME 435. So now you're kind of set up for doing that. So I'm going to change the topic now, and so any questions about this? About how we do single stage flash calculations? Okay, I'm going to move over. To my final topic here before we get to the midterm, and that is a close look here at dilute solutions and Henry's law, a situation which is more often than not applied to the problem of gas-liquid equilibrium. We're frequently interested in the solubility of gases in liquids. By the way, a little bit of reading on that I've indicated here. And that's an interesting problem. It's a little bit different than our standard vapor-liquid equilibrium problem, so we should take a close look at it. Let's look at an example here. A little bigger. So let's imagine that what I have here is a ethanol oxygen system. So I have a liquid phase, which is essentially ethanol. I'm going to call that component 1 in the system. And I have a gas phase here, which is essentially oxygen. I'm going to call oxygen component 2 in the system. And typically what I'm interested in is what is the oxygen mole fraction dissolved in the ethanol, knowing that it's going to be quite a small value, under certain conditions of temperature and pressure. So in the example, let me set T is equal to 25 degrees C, and the pressure, let's let that be 3 bar. That's why I've indicated that up, so we can control the pressure at 3 bar. So actually what I would like to be able to do is solve for everything, but my chief item of interest here is the mole fraction in the liquid phase. But I can solve for the mole fractions of both components in both phases in a systematic way. Before I get started, I should recognize a couple of things, and that is that X2 is generally very small, and the ethanol has a certain volatility, but compared to 3 bars at 25 C, it's not going to be very much. So we recognize also that Y1 is going to be very small. So it's kind of a distorted system, but there's nothing that says we can't use our standard vapor-liquid equilibrium equations to solve this problem. There's equations in which we equate the fugacities of each of the components to one another in the 2 phases that are in equilibrium. But some issues show up when we attempt to do this, so that's what I'd like to address here. First of all, let's look at component 1. Ethanol is my component 1, and I can write F1, and I'm going to use gas phase here is equal to F1 in the liquid phase. So that's the general statement, but now when I write this out, this is going to be Y1P. And in the liquid phase, I'm going to have gamma 1 X1 P1S. Well, right away what I recognize recognize it is that if x2 is very small, then x1 is very close to 1. If x1 is close to 1, what can I say about gamma 1? The Lewis and Randall rule tells me that the Lewis and Randall rule hold for a component present in excess. That's a general truth. So that means if x1 is close to 1, then so is gamma 1 close to 1. So this is approximately just P1s. And my y1 is just equal to P1s over P. You don't see that? So I can determine at the temperature of 25 C that turns out to be just equal to 0.079 bar, which tells me that y1 is equal to 0.079 over the pressure of the system, which was 3, or equal to, what do we got there, 0.026. And oxygen, which is most of it then, is going to be 1 minus that. .974. So that was easy enough. We got it taken care of for component 1, but let's look at the situation now for component 2, namely the dissolved oxygen. And I think, let's see. See if I got it. Nope. We have plenty of time, so I can scroll. Keep on going. So now what I want to look at. What I want to look at is the situation with regard to x2. So I'll write the equilibrium equation here. So for the gas phase, again, we assume we've got an ideal mixture of ideal gases, so no problem, I can write this as Y2P, and now I know everything. I can put a number on that if I want, because I know Y2 as well as the pressure. But now for the liquid, I have to be careful. I've got to write out everything. So it's gamma 2, X2, P2S, P2S, times the pointing factor, and now we have to look at this fairly carefully. The first thing that we have here for the gasity of this 2 and the liquid is here, we have this vapor pressure. What is that? That's the vapor pressure of hypothetical liquid oxygen at 25 degrees C.
So in the previous example, when we were looking for the vapor fractions, the pointing factor ended up being around 1, right? And we used the modified Raoult's law because those two terms became 1, right? But now we're not making those approximations.
Yeah, well, let's look at what would happen there. In the case of Y1, that's ethanol, so we have the vapor pressure of ethanol. And the difference here with the any pointing factor would be here, liquid ethanol, very small molar volume, times the difference between 3 bar and that vapor pressure, so that's at most about 3 bar, so this comes out to be 1 within a couple of decimal places. And it's, we know that the gammas are gonna be 1 because we've got, the ethanol is nearly pure. So there you are.
But why is the pointing vector not
It's not a vector.
I mean the pointing factor not 1 now for the oxygen?
All right, let's think about
Oxygen.
this. I'm just starting to talk about it.
Okay.
This vapor pressure is that of hypothetical liquid oxygen at 25 C. Well, oxygen is of course not a liquid at 25 C. You have to, the critical temperature for it is 154 K. So you have to have, so there is liquid oxygen below that temperature. And in fact, we've got an Antoine equation for it that will give it to us, but that's way down in that range. But that's an untenable extrapolation to try to get up to any value of the vapor pressure of a hypothetical liquid oxygen. Let's say we would agree to do it anyway and find out where we are. Well, we'll end up with a vapor pressure of hypothetical liquid oxygen of about 100 bar or so. That answers your question. I've got here then the pressure of 3 bar minus about 100, so this is now a huge number. And so, and it's gonna be a negative number. So the pointing factor here is gonna be something substantially less than 1. But I really don't know what it is, because I don't know what that vapor pressure is. But it's gonna be multiplied by a vapor pressure, which is enormous. So we really don't know how we're gonna come out on that. That vapor, if it, that the hypothetical vapor now at that pressure, let's say 100 bar, is going to give me a value of the fugacity coefficient for that saturated vapor, which is now very different than 1. And it would require, again, a very large extrapolation to get to it. And of course, we don't know anything at all about that. So the situation, I hope everyone appreciates, the situation is hopeless. Even though it's formally okay, there's nothing that we can do to salvage this situation as it is. So we have to take another approach. And this is something that is fundamentally different. What we know is that the solution is very dilute, and we take advantage of that fact. So if I draw a picture here of a very dilute solution, here are my solute molecules. So solute molecules are far enough apart that on the average they don't even know each other are there.